This is lesson 5 in unit 1. We're looking at limits of transcendental functions. First, we're going to go back and recall some of the things that we've learned in pre-calc about graphing when you do have a calculator, or how you can graph when you don't have a calculator. So we're looking at exponential functions that are written in this format: a times b to the x minus h power plus k. And we want to use the graph to evaluate the limits. So in this case, we see that the limit heading to negative infinity is going to our horizontal asymptote, and that's the k value, which is -3. And on the right, the function is unbounded upward, so there is no limit at infinity, and this is an increasing function. And we can tell it's an increasing function because our b value, that base, is a bigger than 1 value. In example B, we have a negative e to the x minus 1 power. This is a decreasing function as we read the graph from left to right. And as we head to infinity, the negative infinity, we're heading to +2. That's our k value, which is the horizontal asymptote. And then again, the graph is decreasing. So as the x values grow large, the function is unbounded downward toward negative infinity. In example C, our base is 2/3. So 2/3 is between 0 and 1. This is an increasing function because the power on the x, the leading coefficient on the x, is -1. And 2/3 to the -1 power tells us that we have a reciprocal of 3/2, and that the base is bigger than 1, so this is an increasing function. Now, if you didn't have the graph, you could reason through that kind of logic to get a sketch if you needed one. So as we approach negative infinity, our function values are approaching the horizontal asymptote, which is 1, and then the graph is unbounded upward as the x values grow large, and that would be positive infinity for the limit on the right. In part D, we have 1/2 for the base, and this would be a decreasing function, and that's what we see in our graph here. So in that decreasing function, as I move to negative infinity, we're unbounded upward, and then moving to positive infinity, we're bounded by the horizontal asymptote, which is at -3. On part E, we see an increasing function here as you read the graph from left to right, and we have an a value that's -1 and a base of 1/2. So this is going to cause our function to be increasing, and the limit at negative infinity is negative infinity because we're unbounded downward, but the limit on the right is heading to the horizontal asymptote. That would be +2 in this case. And then on part F, this is a decreasing function, and the function decreases when the base is 2 to the -1 power. That gives our base 1/2, and 1/2 is between 0 and 1, so this would be a decreasing function. And the limit at negative infinity is unbounded upward, and the limit at positive infinity would head to our horizontal asymptote at -2. So that's just a refresher from knowledge you have in pre-calc. In example 2, what just happened? We either had functions that were going to negative infinity, or functions that went to positive infinity, or functions that headed to a horizontal asymptote, which is y equals b value. So those are the 3 things that can happen. And when we have this situation where we don't have a calculator We're going to summarize those 6 graphs here on the next page, but these are the behaviors that happen. If A is positive and B is positive, then our function is increasing, and B is the exponential growth factor. If A is positive and B is between 0 and 1, then we have a decreasing function, and B is exponential decay. So like I said, these were the first 6 graphs we had, but in calculus we may need to be able to evaluate without a calculator. So knowing how to read the graph based on that standard form, y equals a times b to the x minus h power plus k. So in this case, let's back up a minute. I don't want to confuse you. In this b, that's my horizontal asymptote at some b value. That is not b the base. So we could say in the equation y equals a b to the x minus h power plus k. We could also say this is heading to y equals k if you thought about it from this point of view. We're not identifying that b as this b. We're identifying that x equals a is a vertical line and y equals b is a horizontal line. So just to clear that up, I don't want any confusion there. And then back to this table, I don't want to spend a lot of time because we just did this graphically, but you can see that we have 3 over 2, it's bigger than 1, and here we have 1 over 2, it's in between 0 and 1. That makes a difference in an increasing function and a decreasing function. And then even though e is bigger than 1, we had the negative a value, which took a normal growth function and turned it into a decreasing function. So our limit at negative infinity was the horizontal asymptote, and because it's decreasing, we had negative infinity as the end behavior to the right. And again, these are just taken right off of the graphs that we just did, so I don't want to belabor that point. Now, in example 3, we want to work through that same kind of reasoning. So here I see my b number is 3/10, so b is in between 0 and 1. That's going to become a decay problem. But the a value is negative, so that's going to reflect our decay problem, or our decay graph, and it's going to cause that graph to be an increasing function. So if you thought about the shape of it, we're going to be over here increasing, and we're going to be bounded at 2. So the limit at negative infinity is unbounded downward. This one, in this case, we know e is bigger than 1, but we have e to the negative 1 power. So if I thought about this way, we would think about it as 1 over e to the x minus 1 power. So this becomes a decay problem, and our function is going to be decreasing. So we've got a decreasing function. And negative 3 is our horizontal asymptote, and this function is going to decrease toward that asymptote. So the limit at negative infinity would be unbounded upward, heading to positive infinity. On this one, we have a negative on the a value, which causes the graph to reflect, but we have 3 to the negative 1 power, which means my base is 1/3. So 3 to the negative 1 causes the base to become 1/3 to the x minus 1 power. And the a value is negative. So I've got 2 negatives. We've got a decay question and a negative a, which is going to reflect that problem or that graph, and that's going to cause our graph to be an increasing function. So the graph would reflect and be down here somewhere below that horizontal asymptote. So at positive infinity, our limit would be heading toward the horizontal asymptote. In example D, we've got the limit at positive infinity for negative 1/3 to the negative x power. So 1/3 to the negative 1 power becomes the base is 3. So the base is bigger than 1. That indicates we've got a growth function. But the a number here is negative. So the a number causes that growth to reflect. And when it reflects, our graph is going to look similar to, let's see, we got 1 is a horizontal asymptote. So we're going to reflect across that graph this way. And the limit at positive infinity is going to be unbounded downward. So we're heading to negative infinity there. Example E, we know that E is greater than 1, so we have a growth function. And we don't really have any issues here. Well, I guess we could just direct substitute on this one. So we would have e to the 2 minus 3 power minus 1. So that's 1 over e minus 1. And simplifying that, we could say we have 1 minus e over e. If this was a multiple choice question, you would want to be able to evaluate that. If this was a piece on a free response, we would just substitute here and call this a safe stop. And then on part F, again, I don't have any issue with just direct substitution. So direct substituting 1/2 to the negative 3, negative 3 minus 1, that's going to become 1/2 to the second power, which is 1/4, and then we would add 5. So 5 1/4 is 21/4 for a limit as we approach negative 3. So these two were not in behavior models, they were just at a specific function or value. And then looking at these to analyze trig functions next, let's think about the limit as theta approaches pi over 3. So we could do direct substitution here, and cosine of 2 pi over 3 is negative 1/2, and we're going to divide that by pi over 3. So negative 1/2 divided by pi over 3 is a safe stop if it was a free response. But if you needed to simplify, we could simplify to negative 3 divided by 2 pi. So either this one or this one would be acceptable. And then at pi over 2, we know the sign at pi over 2 is 1, and we want to square that. So 3 times 1 squared is simply 3. Now, just like some polynomial functions, we can have a function value where the limit will exist even though by direct substitution we have some issue, maybe indeterminate form. And we can see that here. When we substitute pi over 2 for theta, then we're going to end up with sine of pi over 2 is 1, and 1 minus 1 gives us a numerator of 0, and the cosine at pi over 2 is 0, so in the bottom we have 0 squared, and that likewise gives us 0 for the denominator, so we have indeterminate form here. Indeterminate form. Well, my pen is misbehaving. But you can see in the next slide that the graph of that function, the sine of theta minus 1 over cosine squared theta, we do have a value at pi over 2. So we can simplify. Let's factor this first. The sine of x minus 1 and cosine squared, we can think of that using the Pythagorean identities as 1 minus sine squared. And factoring the denominator, the sine of x minus 1 divided by 1 plus sine x times 1 minus sine x. So in this case, I can remove this factor, sine of x minus 1 and 1 minus sine of x. Those are the same factor if we just consider this switched around as negative sine x minus 1. So that factor removes this factor, and we just have a factor of negative 1 in our numerator. So negative 1 divided by 1 plus the sine of x. And then if we wanted to back up to our previous problem, now I can substitute pi over 2, and our value at pi over 2, the limit, would be 1 plus the sine of pi over 2, which is 1. So the value of the limit at pi over 2 did exist. We just couldn't do that by direct substitution on this previous problem. So we do have a limit. We just didn't know what to do yet. And the Pythagorean identities helped us out there. So this would be our simplified form after we factored. And I guess pi over 2 must be right about in there for the value of the limit at pi over 2. Let's see. Then in example 7, we're going to use those new skills to evaluate each limit below by first rewriting the function and then using identities. In the first one, cotangent can be written again as 2 times cosine pi over 2, and then cotangent could be thought of as cosine divided by sine, and then using direct substitution at the same time. Cosine at pi over 2 is 0, so we have 2 times 0 times 0, 0 in the numerator, divided by 1 in the denominator, and our limit is heading to 0 at pi over 2. In part B, we've got sine times cosine, and tangent, we're going to think of tangent as sine divided by cosine. So when you remove this and multiply by the reciprocal, we're trying to take the limit. Whoop, I'm using bad notation here. Want to keep writing the limit until you've evaluated. So we are looking at cosine divided by 1 over cosine, which would be the cosine squared at pi over 4, and the cosine at pi over 4 is radical 2 over 2, and when we square radical 2 over 2, we're going to end up with 1/2, because that's being squared. So this becomes 2, and the denominator becomes 4, so our limit is headed to 1/2 as theta goes to pi over 4. And then part C, we have the sine of theta over 3 theta and multiplied by cosecant. Well, we know sine times cosecant is just 1, so our limit as theta approaches pi is 1 over 3 theta, and the limit would be 1 divided by 3 pi once we substitute pi in for theta. So direct substitution. So our question is, have you discovered a pattern in all of this yet? If you always try direct substitution first, 3 things are going to happen. You're either going to get a number value, you're going to get a number that's divided by 0, so a number in the numerator and a 0 in the bottom, or we're going to get 0 divided by 0. Now this one is called indeterminate form. And when you get indeterminate form, you need to do one thing, and that is to inspect the one-sided limits. Indeterminate form. So when you get indeterminate form, you inspect the one-sided limits and think about, are they going to infinity? Are they going to negative infinity? Or does the limit not exist because they're going in different directions? So just as a little note, you want to ask yourself, is this what happens? Is this what happens? Or do both things happen? So you have to answer does not exist. Now when you get this one, a number divided by 0, you've got to think about which way these go. Again, am I unbounded up? Am I unbounded down? Or does the limit not exist? Also, when you get indeterminate form, that's an indication to do something. You either want to factor, you want to cancel, you want to rationalize, you want to analyze. So this is my I got to do some more work step right there, just like we saw on the trig graph. So either factor and cancel, try to rationalize the numerator or the denominator, or like we said, analyze it by inspecting one-sided limits. Now later in the course we're going to learn about L'Hopital's rule, and you're going to like that because it'll be a quicker way to evaluate functions. But for right now, you might want to memorize these special trig functions and possibly even stop the video and graph the sine of x divided by x and graph 1 minus cosine x divided by x, and just take a look at how both of the functions, one of them is going to 1 as x goes to 0, and the other one's going to 0 as x approaches 0. So you may want to memorize those. This, you need your calculator. So pause the video and get your calculator out and evaluate these for each one of the values in the table, and then come back to check with me. Now I've looked at each one of these functions one at a time, and I noticed at my target number I have a do not exist for each one of these. But if we consider what's happening on the left and the right, you can see this limit is approaching 2. And this limit is positive y value on the left, but a negative y value on the right. So in this case, we have a does not exist. That would be more like a vertical asymptote. And then in this case, both sides are positive. So it looks like the function is heading to 3/4 as we approach 0. And then this one, the same thing. On the left, we have a negative y value. On the right, we have a positive y value. So in this case, we're does not exist. But then you've got to consider that the two properties we just looked at, so this is where the analyze part comes in, starting off with this rule right here. If I take letter B and rewrite the argument cosine 3 theta minus 1 as the opposite of 1 minus cosine 3 theta, then you can tell this is similar to the rule right here, only I have an argument of 3. So to make that balance out, I would need to multiply the top and the bottom by 3 in order to use that rule. So I could multiply the bottom by 3 and the top by 3. That would give us negative 3 in the numerator. And this rule here is 0. So negative 3 times 0 is 0, which means our answer based on the table appears to be does not exist, but in actuality, a better answer would be the graph goes to 0. Now, can we think of this the same way? So 1 minus cosine 3 theta over 2 theta, because it appears from the table that there's no limit. But if I can make this turn into a 3 times a theta and just kind of move that 2 as a factor out, all I have to do is multiply the top by a 3 and the bottom by a 3. So we have 1 minus cosine 3 theta divided by 3 theta. So this limit is 0, and I have a 3 over 2. So this limit of 0 times 3 over 2 is also going to give me a 0. And that's the reason we said you need to be able to analyze. So one of the tricks to these trig identities is just to be able to analyze, even though you had a table. Now, if you had a graph, it would be easy to see from the graph that they were heading to 0. So in these last few, here's some algebraic manipulation. So we've got the limit as theta goes to 0, and I've got 3 sine 5 theta over 2 theta, and I need to have 5 theta on top and bottom. So I want to multiply the top by 5 and the bottom by 5. So just a little bit of manipulation. We've got the limit as theta goes to 0. So 3 times 5 gives me 15. And I'm going to leave the 2 here and put this 5 with the theta. So we could have the sine of 5 theta divided by 5 theta. And that property, the limit as theta goes to 0 of this property is 1. And 15 over 2 times 1 means our limit is going to 7.5 or 15 halves. In this one, we want to break this up maybe into 2 separate things. So I've got a single term denominator. I can break up the addition and leave the first piece as the limit as theta goes to 0 of 1 minus cosine theta divided by theta. So we know this property. And then I can add the limit as theta goes to 0 of sine of 3 theta divided by theta. Oh, I'm really out of room there. So in this case, we have a 0 for the limit. So this entire piece is going to go to 0. But in this piece, we can multiply the top and the bottom by 3. And that's going to give us 3 times the sine of 3 theta divided by 3 theta. And we're looking at the limit as theta approaches 0. So this is going to 1. So we have 0 plus 3 times 1. So 0 plus 3 times 1 gives us the limit at 3. So just a little bit of algebraic manipulation. Then our very last example is looking at the squeeze theorem. So we want to explain why you can't use the product limit law. Well, the product limit law, we could say the limit as x approaches 0 of x squared times the limit as x approaches 0 of the sine of 1 over x can't be used because this limit doesn't exist. This limit does not exist. So we can't use the product limit law that says if you have the limit of a product, you can take the product of the two limits. But when one piece doesn't exist, we can't do that. That means the next thing we want to do is we want to think about the range. This should say the range of the sine function. And the range of the sine function oscillates between -1 and +1. So if we set this up, -1 is less than or equal to sine of 1 over x, which is less than or equal to +1. If we multiplied through by x squared, then we'd have -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. So I'm multiplying each term, this term, this term, and this term in this inequality. I'm multiplying each of the three pieces by x squared. This is my original limit. And we know that the limit going to 0 of x squared is 0. And we also know that the limit going to 0 of -x squared is also 0. And we could say since the limit as x goes to 0 of x squared is the same as the limit going to 0 of -x squared, then we can use by the squeeze theorem, we can say that the limit of the product, squeeze theorem, that the limit going to 0 of x squared times the sine of 1 divided by x is also 0. Okay, so we used that property. We set up, we knew some things about the sine of x. The range for sine was between -1 and 1. So the sine of 1 over x, when I multiplied through by x squared, we created our original function. We knew that this limit was 0, or this limit was 0. We knew the other end was 0. And just like the picture showing, if they're both heading to 0 and this is our x squared sine of 1 over x, then they've got a squeeze in between there. And then the last example, 11, would be one that you could try. And we again know that cosine oscillates between -1 and +1. So I would recommend you turn off the video and give this a try and come back and check your work with mine. And here you can see I've set it up similar to the other one, only keeping things uniform. I took the limit of the first piece, the limit of the middle piece, and the limit of the second piece. And since we knew this limit went to 0 and the right limit went to 0, then we could make the assumption that the limit in the middle was heading to 0 by using the squeeze theorem. That's the end of our lesson.